Hello, everybody. Welcome back to another super easy strengths of materials problem. This one's going to be on the equilibrium equations once again. And I picked this problem just because it looked like it would be fun to solve. And it's just a super easy problem where it asks us to find the intensities of the distributed load. And we have a unique case where we have a triangular distribution underneath this concrete footing. And the reason that's happening is because our column is offset from the center of this footing, which means that we're having a higher intensity on one side of the footing with respect to the other. And this problem is super easy. I'm going to show you step by step my thought process for it. And the problem goes as follows. It says we have a pad footing that uses a 1200 or 12,000, sorry, 12,000 pound concentrated load to support. And it wants us to find those intensities for equilibrium. Now, what do we remember about equilibrium? For every action, we have an equal and opposite reaction. So if we have 12,000 pounds here, that means that this distributed load times the area that it covers should equal that opposing force. And in order to do this, we need to understand some things about the distributed load, which is that we have a trapezoidal distribution here, where we have two different intensities that need to be divided into separate segments. What do I mean by that? Well, when I look at this, I see a triangular distribution, which is on top of a rectangular distribution. And that rectangular distribution is going to have a height of, or an intensity of W2. And then this triangular distribution is going to have a peak intensity of W1, and then come all the way down to an equivalent of 0. So let's highlight those shapes in this distribution here. Alrighty, so now we have the distributed load segmented. The next thing that we need to do is understand that each of these distributions can be simplified into a resultant force. For a rectangular distribution, that will act directly at the center. And for a triangular distribution, it depends on the shape of the triangle. So with respect to this left edge, for example, we know that that resultant is going to act 1/3 of the max distance of this footing or this distributed load. So it's going to be 1/3 of this 35-inch. But let's draw these forces and let's calculate what those values are going to be. All right, so now I have it all drawn out. We can see exactly what I'm talking about here. We have the two resultants, the red one representing the rectangular distribution and the blue for the triangular. And they both have a distance x with respect to this edge that I've arbitrarily chosen so that we can do some of these calculations. So first things first, let's go ahead and solve for these unknowns. First thing that we can do is figure out what this x value is. We know that it's going to be 1/3 of whatever the total distance is. So 1/3 of 35 inches. Then FR is going to be obviously the area that this distributed load is covering. So we're taking W1 minus W2 to get this intensity between these 2 points, between the top of the rectangular distribution to the top of the triangular. So we know, first of all, we have 1/2 for triangular. We're taking W1 minus W2. And then what does this cover? What area or length is this covering? It is the total length of the distribution. So that is 35 inches. And then we do a similar thing for the rectangular distribution. We have the total length being covered for the rectangular distribution, except now we're not going to have a half here since it's rectangular. And the peak intensity is just W2. So you have W2 times 35 inches. Then for x2, obviously it's going to be 1/2 of 35. So we just write that down right here. However, we run into a problem now. We don't know how to get these variables still. We just have a bunch of things that we solve for, but we don't have a way to solve it. Well, that's where the beautiful equilibrium equations actually come in, because we can take a moment about one of these unknowns. And since we know that moment is force times distance, if we take it about, for example, this point here, then we can neglect FR1 in our calculation for that moment equilibrium because we're taking it about that point. There's no distance between the force and the point of reference. Alrighty, so now we have a reference point drawn on this diagram, and I've picked this point at FR1 to simplify our problem. Just to reiterate, we are doing this because FR1 will be acting directly at a reference point, meaning that there's no distance. And since moment is force times distance, this is going to end up not influencing our point of reference, leaving us with just FR2 as an unknown here. And the reason that I also picked this point is because FR2 only has one variable, W2. If we did the opposite and we took the reference point here, FR1 would end up having two variables that we solve for. Wouldn't really help us in the long run. So that's why we picked this point. So we have two different forces that we need to consider for this moment equilibrium. And that first distance is going to be this yellow line here, which is XA1. And we know what this distance is going to be. The distance from the left edge of this footing is going to be 5 plus 9 to get to that 12,000 pound force. And we're taking away that x1 that we solved for previously because that is the distance from the edge of the footing to our new reference point. So that formula is going to look something like this. We have 5 plus 9 to get to this force, and we're taking away the distance behind our reference point, which is simply going to be x1. Solving that, you have 14, subtracting this number right here, 1 over 3, 35, and that's going to give you approximately 2.33 inches. We do a very similar thing with this purple line here, which is now the distance to FR2. And we know where this is acting. This is halfway uh, to the distributed load, and that is going to be 35 over 2, which we already solved for. And we're taking away x1 once again. So in formula terms, it's going to look like x2 minus x1. And that's simply going to be 1/2 of 35, subtracting 1/3 of 35. Solving for this, you're now left with 5.83 inches. Now we can finally go to our moment equation, where we have the summation of moment at A is equal to 0. Set up our convention here, and then we can start solving. How do we do this? We need to consider the force times the distance for both of these forces here. So first things first, we have the negative 12,000 pounds since it's going clockwise. So 12,000, that is times our distance that we solved for right here, 2.33. Then we also have to consider FR2. So that force is going to be a positive since it's drawn in the counterclockwise direction. We have W2 times that 35, and then this value right here, that purple, which is 5.83. And solving for this, you can rearrange it to get W2, which is equal to, let me just find the number here, 137.0 pounds per inch, which is approximately equal to 1.64 kip foot. Alrighty, so now we've cleaned up the problem. The only thing left now is to figure out this W1, and it's just going to be a very simple sum of forces at Fy in order to isolate this unknown variable. So let's see what that looks like when we do that. We have Fy, or the summation of forces at Fy equals to 0 for equilibrium. We're going to have something that looks like this. We have the negative 12,000 pounds. Then we're going to be following that up with the FR2, since we know this one. And that's going to be 137.0 times the 35. And that's this formula right here that we're just plugging into. And we have the FR1 that we need to plug into as well. So that's positive 1/2 W1 subtracting 137.0. And that's also times 35. Closing the bracket, and then rearranging all of that nasty mess, you're going to be left with an answer of 548.7 pounds per inch, which is approximately equal to 6.58 kip foot. And those are your two final answers for this problem. I hope the visual helped. I know it seems a little bit confusing if you don't really know what you're doing. But once you get a good idea of the picture, then it's really easy to figure out these types of problems. So I hope this helped.